Afternoon, everybody. Thank you for joining us on today's Adding Value program. We've got a really busy schedule ahead of us this afternoon. So we've got some great presenters from across the automation industry. We're really lucky to be so well attended, and we're really lucky with some of the people that we have actually presenting for us today. So we're going to hear about some new products, we're going to hear about some new software, some innovations in terms of technology. Each of the presentations is going to be kept to about 20 minutes long, and then we're going to have time after each presentation as well for some questions and answers. So anybody with any questions, please put them into the Q&A section, and then what we'll do is we'll pick them up at the end of each presentation as well. So all the questions will be answered, and we'll do that at the end of each presentation. So next up we have Stuart Bratton from Danfoss, who's going to be joining us talking through condition-based monitoring. Hi, Stuart.
Hi, Dan. Afternoon, everybody. See, everybody's rushing through their presentations, and there's a complete lack of questions. It's because everybody wants to get to the beach in the sun. So I assume that it's as gloriously sunny everywhere else as it is here in the southwest of England today.
It's close enough. It's close enough. 26. That's hot enough for me when I'm working.
Okay. For those that don't know me, I am Stuart Bratton. I'm the applications manager at Danfoss Drives here in the UK. I'm going to talk about condition-based monitoring, really specifically on our range of drives, but maybe touch on the subject generally to some extent. Please, if you've got any questions, don't be shy. Put them in the question and answer session. If you do want to get to the beach, I'm quite happy to answer them later. So let's see how we get on today. If we think about equipment in a plant, there are various ways of maintaining this, and it's surprising how the number of plants I visit today, I still see people who unusually use a reactive approach to maintenance. So they run stuff until it breaks. I'm sure nobody on the call today takes that sort of approach, but it does happen. Obviously, that's the most ineffective way, really, of maintaining assets. The next best alternative is to use some sort of preventative maintenance scheme. So plan a schedule of when you're going to look at equipment, maybe change filters and things on drives on a regular basis. So sort of, preempt stuff that might fail and plan something into a schedule of works that you've got the time to take those actions and keep equipment running. So that's better than running it till it breaks down. But next on our sort of sliding scale of effective ways of maintaining equipment is what we're going to focus on today, and that's our condition-based monitoring. So this is where really we monitor the system in some way and use some sort of rules to detect a change in the operating conditions, and that change in operating conditions signifies that there's a potential failure looming in the future. And all of these sort of maintenance strategies are all working on the principle of the earlier we can detect a possible failure in the future, the more effective our maintenance of this equipment is going to be, in that we can schedule the work in, we can make sure we've got spares, whatever, and we keep our system running as effectively as possible. So I'm going to talk about condition-based monitoring, but if we go beyond that, it's possible to sort of analyze the condition of the equipment, maybe using machine learning and things like that, and I'll talk about that in a bit more detail in a second. And we can use, more advanced computing power to predict future failures by looking at trends in data. So condition-based is we've spotted an actual change in some sort of variable in the system, whereas predictive maintenance is the change hasn't happened yet, but by analysing the data, we can predict that it's going to happen at some point in the future. So to do our condition-based monitoring today, it's possible to do some of this in a drive. I'll quite often compare a variable speed drive to a mobile phone. Years ago, we all used a phone to make a telephone call to somebody, and if we were really lucky, we had a phone we could play Snake on. But nowadays, you don't just use a phone to make a telephone call. It's a very powerful processor that can do all sorts of functions, and the same is true for a drive. It doesn't just spin a motor. It can process all sorts of data. So inherently in the operation of a drive, we're already monitoring current, we're monitoring supply and output voltage, we're monitoring the temperature of the drive, and we're all used to seeing, let's call them instantaneous faults on a drive. It could be over current, over temperature. We might think of that as being flight recorder data. So in the same way that an aeroplane is capturing all sorts of signals from the plane and recording that in a black box, the same sort of thing is going on in a drive. And that gives us instantaneous information that we react to. And then this is where our reactive maintenance comes in to fix the problem. But if we process this data in some way in the drive, so for example, if we're recording current that's going out to a motor, rather than looking at the RMS value of that current or the peak values, maybe the drive can actually analyze the frequency spectrum of the current. Is there, the components that make up that current, have they changed in some way? Or we can look at the amplitudes of specific frequency components. Again, detect, are those changing in some way? We can do statistical analysis in the drive of signals. So by processing that in the drive itself, we don't need any external equipment. We've got some drive processors, like I said, are very powerful today. We've got a lot more memory. Memory is cheap. Processing speeds are very high. We can do a lot more in the drive than just spin a motor. So we can use the drive, detect a change of some type in these signals, and that gives us our condition-based monitoring or maintenance. And as I already mentioned, if we took that data and captured it long-term in some way, we could use analytics to then predict what's going to happen in the future. And today, we might use the power of cloud computing to do that analytics, or we might have a very powerful PLC maybe that's capable of doing that. It probably won't be long before I'm sat here again talking to you about how we're doing analytical evaluation of signals in the drive itself as well, and also predicting future failures. So, although I'm going to talk about what we call CBM in Danfoss, condition-based monitoring, which is an add-on, let's say, to a standard drive, we actually have some condition monitoring that's part of some of the drive's standard functionality. So if we took and this is maybe if you're sat in an office today, sweltering, maybe this is particularly relevant. So our FC102 HVAC drive, for example, has the ability to monitor the amount of power or energy that's required to produce a specific flow or volume of airflow. And there is a standard EN 16798 that relates to the energy performance of buildings. So anybody on the call today that maintains or even designs systems for buildings is probably familiar with this. Typically the SFP rating for a new building might be like 1500 or lower, for example. Our drive can actually monitor what sort of energy is needed to shift the volume of air and display this on the keypad. Well, monitoring and just displaying a value is one thing, but what we can also do in the drive is we can what we call baseline that SFP value. So we can record in the drive can store internally what's the amount of watt seconds required to shift the particular amount of air. And what this allows the drive to detect, like I said, when it comes to condition-based monitoring, we're looking for changes in behavior or behavior of signals of the drive. So if the drive detects, well, hang on a minute, all of a sudden I'm now requiring more power to generate the same airflow, that indicates a problem, and it probably indicates that the filters in an air handling unit, for example, are starting to clog up. So in an FC102, there are parameters that let you define, well, how much would it actually cost me to replace a filter? How much, what is the kilowatt hour energy cost? And the drive can calculate every day, well, this is how many more days I think it's going to take before it actually becomes more cost effective to replace the filter than it does to keep running the drive. So that's just one very simple example of how we can do condition-based monitoring in a standard drive. But we have some more, let's say, advanced condition-based monitoring features in our drives. These are available through a licensing scheme, so you can either order drive with the CBM feature, or if you've got a drive typically that's newer than 2018, so it has to have a specific sort of version of control card, let's say, you can retrofit or effectively download or enter a license code to enable this feature. So our licensed CBM features include a number of functions. The first of which is something we call stator winding monitoring. So this uses a current signature analysis, so like a frequency spectrum analysis of the current going out to the motor, and it's able to detect a change in that current signature. It's so advanced that you can actually detect a short circuit between two adjacent coils in a motor winding. So anybody that's got any knowledge at all about motor insulation breakdown will know that it's not typical for it to just catastrophically fail instantly. What tends to happen is that two adjacent coils will overheat or fuse together initially, and then obviously that leads to increased heat in that area, and eventually the rest of the windings start to fuse together, eventually ending up in some sort of catastrophic failure. So this initial fusing of two adjacent coils could be weeks or even months ahead of the final failure. And the drive is able to detect that. So that's now giving you plenty of time to get a spare motor in place if you haven't got one already. There are parameters to sort of adjust the algorithm to account for the effects of a weak supply to the drive. We very rarely touch those, and this technology works with every sort of motor type that you can think of, really. Even if you've got a drive that's powering multiple motors in parallel. The same sort of technology is also capable of detecting problems with sine filters. So if you have a sine filter connected to the output of the drive, for example, you've got an installation with a long motor cable, so a borehole pump, for example, then a similar feature in our CBM suite can detect a problem with with the sine filter, so the capacitors, for example, starting to fail in a sine filter, will result in a change in the current signature that the drive is producing. So our second CBM feature is the integration of sensors to the drive. And I use the word sensor generally rather than just vibration sensors. Vibration sensors are the most common type of sensor to connect for some sort of condition-based monitoring, but we're not limited to vibration. Really, we can connect any type of sensor at all to the drive, as long as it is a 4 to 20 milliamp format. We don't really care what we're measuring. The reason that we want to connect the sensor to our drive is that it gives us the ability to correlate the measurement data, let's say it's vibration, with the speed of the motor. If we were to use an externally mounted sensor on the load, for example, it may not necessarily be aware of the speed the motor's rotating. It's just arbitrarily measuring vibration levels. But with the sensor connected to the drive can record, I mentioned the word earlier, a baseline. So, the normative recording of what is the expected sensor signal for a range of motor speeds. And as I've said before, the drive can then process that data in some way. We can connect up to 4 sensors on the drive. The limitation is only really how many analog inputs are available on your specific drive. And of course, there are option cards available to expand beyond the 2 analog inputs that we have on a drive as standard. If we think about vibration monitoring specifically, we're not monitoring in the frequency domain. We're measuring, let's say, an RMS vibration again, and we're correlating that against any particular motor speed. So the sorts of things that we're going to detect are unbalanced loads or eccentricity or looseness or misalignment of shafts, depending on the type of sensor that we use, whether it be a velocity or an accelerometer type sensor. It's possible to also detect higher frequency vibrations, let's say, that are indicative of potential bearing failure. But the important thing really, as I've mentioned it a couple of times, is this correlation against speed. We're not just capturing a fixed level. We're somehow matching the vibration level or the sensor signal against the motor speed. I'll come back to that and show why that's important near the end of the presentation. The next function is something we call load envelope monitoring. So here the drive, again, makes a baseline, so it learns what is the expected RMS output current for any given motor speed. And in this case, then we can program into the drive thresholds above and below that expected current to give us an indication of when we're pulling more current than we might expect or less current. So this gives us the opportunity to detect things like fouling in pumps, or there's a broken impeller, or if maybe a gearbox is starting to seize up on a conveyor. Who knows what it is? We don't really care. The drive's not going to analyze the problem for us. It's all about detecting these change in operating conditions and flagging up as early as possible to somebody who can investigate the problem that something isn't right. Because we are able to analyze the signature, let's say, of the current that's going out to the motor, this also gives us the ability to detect cavitation in a pump. So if you were to run a pump across a range of speeds with absolutely no cavitation, we would get a particular, I'm going to call it, signature of the current. So the drive will analyze all the frequency components of the current, and it will establish, okay, these are our normal currents. What we see with cavitation from a pumps, we get our little air bubbles building up and exploding and damaging our impeller, is that disturbance to the impeller shows up not only audibly, I'm sure a lot of us on the call have heard cavitation from a pump, but it also shows up in the current that's going out to the motor. So the drive, without needing any additional sensors externally, it's purely using the current sensors that are already in the drive as standard. It can detect this change in current signature, and it's able to identify that the reason for that, because of the very characteristic nature of cavitation on the current signature, is able to detect that that's cavitation and indicate that to the user. Now, we could just leave that as indication, and I'll talk about how we indicate the effects of CBM events to users a bit shortly. But with cavitation detection, there is an option to also allow the drive to automatically adjust for this. So after a programmable amount of time, so we say, okay, we think we've seen cavitation for a particular amount of time, we can sort of program into the drive its own ability to then adjust its output speed to try and get rid of that cavitation. So we don't need any input from an external control system or an operator. The drive can sort of automatically sort of get rid of the cavitation, and at some point it will then sort of try again and see if it's able to resort back to its original speed reference without the cavitation occurring. Of course, if it occurs again, then it just won't run at that speed. And it will record and provide information to the user of let's say, cavitation areas in the operating zones. So I probably mentioned most of these. You can enable and disable this. You've got all sorts of programmable features about the thresholds, how long it has to be cavitating for before it takes an action. And I said we don't have to take avoidance actions, but it's probably a good idea if we do. But you have the flexibility to decide how you want the drive to operate. So how does CBM generally work across all these functions? So internally, the drive measures these signals and sort of turns them into, let's say, a 0 to 100% value. And when we initially set up the drive, we have to baseline each of the functions. So there'll be a baseline measurement for the stator current, a baseline measurement for the up to 4 sensors. Let's call them vibration sensors for purpose of this talk. And it will baseline the load current, and if we're using cavitation detection, it will do that. And if we're doing sine filter measurement, it will baseline that as well. And then the drive can automatically generate thresholds based on these baseline measurements, so that we can set according to relevant standards for condition monitoring. We can automatically generate 2 warning levels and an alarm level. These are all sort of manually adjustable, so you've got full flexibility. So really, how deep do you want to dive into the system? If you want to manually adjust the threshold levels, you can. If you just want the drive to set the defaults, it can equally do that as well. And these baselines can either be done on the spot. So you tell the drive, I want you to start and run from this speed to this speed and baseline the measurements on the spot. Or if you want to leave the process running over a longer period of time to generate let's call it a better average recording of all the data, then you could leave it running as long as 6 months, gathering data before it finally generates the baseline. The key thing is that once you've set it up and enabled, whether you want it to take an alarm or just generate a warning, the drive is now continuously monitoring this. So you haven't got some guy coming into your facility, once a month or once a quarter, going around connecting up his vibration monitoring equipment and taking readings and just telling you on the day whether there's a problem or not. The drive is monitoring this 24/7. So just to give you an idea of what it might look like in our programming software, so the drive programming software, the sort of dots you see on this graph are like the mean sort of peak and minimum values that it recorded. Let's say this is vibration, and then the yellow, orange, and red lines of the thresholds and the alarm levels that maybe the drive has automatically generated based on the data it captured when it ran the baseline level. And you can set either absolute values for the thresholds, or you can offset the thresholds from the baseline, or you can make it a factor, so 1.2 times the levels that were captured during the baseline. Completely up to you. Like I said, most people probably just let the drive set the baselines, but other people with a lot of experience of vibration monitoring, for example, may have other ideas on how they want to set up the thresholds. So to give you an example of why this correlation against speed is such a great feature, is that if we were to just imagine we'd taken a baseline, and these are our this is actually a real life application. So this is a drive in one of our buildings in Denmark where we manufacture the drives. So we have condition-based monitoring on drives that are running in our own factory, of course. Why wouldn't we? And we can see there is a bit of a resonance at about 1250 RPM on this particular system. And if we were to put an external vibration monitoring sensor on this particular application, we might have to set it up so that it didn't generate a warning unless we exceeded something like, 21, 22 millimeters per second of vibration. But in this case, if we were running the fan at 725 RPM and the vibration was to increase to 15 millimeters per second, then our external sensor just wouldn't throw that up as a problem at all. It's only going to detect a problem when we exceed 22 millimeters. But the drive, obviously, it's it's correlated this data against speed. It's capable of saying, well, actually, at 725 RPM, this 15 millimeter vibration level is unusual. That's a problem. And it'll either throw a warning or an alarm, depending how we've configured the drive. So I said I would talk about the possible interfaces to CBM. So the most basic interface is the keypad on the drive. So you don't have to do anything with this at all if you don't want to, other than just get a notification through the keypad. So it will throw up a warning or an alarm and display that on the screen. Probably most people aren't going to just do that. We live in a bit more of a modern world, and just wandering around looking at drive keypads. Maybe we'll connect some outputs to a PLC or a BMS system. So we could configure a digital output on the drive to tell a PLC or a BMS, yeah, I've got a problem with the vibration sensor, or I've got a problem with the stator winding on the motor. So that's quite a simple interface. We might extend that and say, well, actually, our drive's got Ethernet on it or some sort of field bus. Why not network that up to a PLC of some description? Maybe we'll even take that data out to a SCADA system or an HMI. And of course, we have function block libraries that allow us to very easily read not just the status information. So, there's a, let's call it a status word that's got bits in it that tells you the status of each of these CBM channels. But if you really wanted to, you could also pull the threshold data out of the drive. You could pull the real-time values out of the drive. You could do your own effectively monitoring of the system. I'm going to call it real time. Obviously, it's not real time because you've got delays over the network pulling it out to the PLC, but at least you can visualize this data in the same way that you can visualize it in our drive programming tool. The last option, and it's not an essential option, so we don't need any sort of cloud interface at all to do this analysis. So we're not using sensors with batteries. We don't have to worry about batteries running out. We don't have to worry about secure connections to the cloud. The drive is locally processing all of this itself. But if you want to take it out to the cloud, you could use an IoT gateway of some description. Of course, Danfoss have these. Connect that to the drive, maybe through a serial connection, Modbus RTU, for example, and then pass this data up to a cloud. And of course, Danfoss does have a cloud remote monitoring service, which we can offer customers as well as our own gateway. And from there, you either just use that cloud directly, or of course, there are APIs available for cloud-to-cloud data transfer. So that's the end of my talk. I just reiterate, any new drive can be ordered with CBM. We have a lot of OEM customers that now standardize on that, everything they do, because it's such a great feature. And if you have old Danfoss drives, contact Dan. It's quite possible that those could be upgraded to include this feature.
Excellent. Thank you very much for that, Stuart. That's been really good. We have had a question which with regards to supplying of case studies. With regards to this. So yeah, if we can get some case studies for this sent through, we can obviously share that with everybody as well.
Yeah, I can do that. I would say if you quickly Google Danfoss CBM condition-based monitoring Heineken, you'll find a great case story online. But yeah, I can provide more.
Perfect. Thank you very much.